This is section 3.2, page 6. Now we're going to look at what's called the symmetric difference quotient and the numerical derivative. So we've seen this graph before. We're going to look at it in a little bit different way today. So we have some point A here, and we're interested in finding the slope of the tangent line at A. So we'll go ahead and draw the tangent line in here. There's my tangent line. And what we did before is we took a second point, say out here, and we looked at the slope of the secant line. We'll get a secant line here. I'm just going to draw it as a chord. But this secant line, and we talked about we could use the slope of the secant line as an approximation of the slope of the tangent line. And it's not awful. I mean, it doesn't look great here because kind of we're zoomed in pretty far. But that's a method that we did. And we would have called this, say the distance between here and here is h. So this would be a plus h. So we can see visually that those slopes are a little bit different. But as we let h get smaller and smaller, we knew that those slopes became closer and closer in value. So what we did is we said for very small values of h, we know that f of a plus h, which is up here, f of a plus h, and let's say f of a right here, f of a plus h minus f of a all over a plus h minus a, change in y's over change in x, is, for small values of h, a pretty good approximation of the slope of the tangent line. I'll write that of f prime of x. We're used to that notation now. Okay, but here is the revelation for today. If we look at a point that's exactly the same distance to the left side of A, so I'm going to go h over here. This would be a minus h. My function value over here, a minus h. And if I look at the slope of that secant line, my drawing's not exactly perfect here, so I'm going to cheat a little bit. But if I look at that secant line, you can see that the slope of that is much better. And in fact, if I had drawn it right, the slopes would be pretty much the same because they would be parallel lines. So for the same h value, we're going to look at a symmetric set of points around A. So if I look at the slope now, change in x over change in y, I get f of a plus h minus f of a minus h, so that's the change in y values here to here, over a plus h minus a minus h, the change in x values here. That's going to give me a better approximation of the derivative, and I'm going to even write that as f prime at a, the slope of the tangent line at a. And if we take a look at this, this is actually, this is a slope function that gives us a good approximation and doesn't even require limits. So that's kind of what's nice about it. This is actually called the symmetric difference quotient. Symmetric difference quotient. And we'll clean it up just a bit. F of a plus h minus f of a minus h. Can't do anything with the numerator. But the denominator, if we take a look, the a's cancel. And then we get h minus negative h, so it's all over 2h. That is our symmetric difference quotient formula. And gives us a very good approximation of the derivative at a without even requiring limits. You can still think of h getting smaller and smaller. As h gets very, very small, then this secant line is much closer to the tangent line, and gives us a very good approximation. So I'm actually going to write that out as well. As h gets sufficiently small, And by the way, you want h to be small so that you don't have to deal with other features of the function that may influence the result here. So as h gets sufficiently small, the symmetric difference quotient, can I abbreviate it like that? Symmetric difference quotient approximates the slope of the tangent line at the point x equals a. Okay, so if we talk about this value of h, how small does it need to get? Well, that would be called the tolerance, and we can mess around with that a little bit and see how small we want it to be. I'm going to write how small we want h to be is called the tolerance. And on the next page, we'll do some practice problems with that.